All right, so ladies and gents, from Friday, these are the 5 questions that I think you guys should know, or if I at least say the answers to the questions, then maybe you can be like, oh, that sounds familiar, right? That's the goal. So number 1, the question is, what 2 forces are involved with our nucleus? Does anybody remember any of them that we had mentioned last? The which one? Yes, so we had the strong nuclear force and electromagnetic. Good. So if we have the strong nuclear force, that means it's really, really strong. That is our attraction between the protons and the neutrons. So between the protons and the neutrons, there has to be kind of a force gluing them together, right? To keep my nucleus as a whole. But there's this other force called the electromagnetic force. So with the electromagnetic force, that one says opposites do what? And likes repel. So opposites attract, likes repel. Within my nucleus, I am going to have a lot of protons which have what charge? Positive, right? So with my first one, strong nuclear force makes for a stable nuclei. The electromagnetic force does not. The electromagnetic force would want to tear apart my actual nucleus, okay? So it's not a good thing. It's not a good thing, right? Because those protons, they don't want to be by each other. So when I get too many protons, they're going to try to push each other apart, right? So number 2 says, what can cause the nuclei to be unstable? I either have too many, what? What particle? Protons, good. Or maybe I have too few, who? Yeah, neutrons. Or just in general, the electromagnetic force is greater than the strong nuclear force, okay? So those are the 3 reasons why our nucleus might be a little unstable. Okay, so if it's unstable, again, there's either too many protons, there are too few neutrons. Remember, the neutrons kind of help space out the protons, okay? Or just in general, the electromagnetic force is going to be greater than the strong nuclear force. So ultimately, no matter what, number 3, we undergo nuclear decay to be, same ideal as always, to be stable. Good. So it's going to keep decaying. Remember we said we had alpha, beta, gamma, and neutron emission. So it's going to keep losing protons and losing protons and losing protons. Maybe losing some electrons, maybe losing some light as a release of energy. Okay? But ultimately, it's going to keep going through a decay sequence until it is stable. Okay? So on, what's it called? On Friday, our half-life. On Friday with our half-life. Yeah, we had talked about M&Ms and we said, okay, is it going to decay? Is it not going to decay? How fast will it decay? So we had this idea of half-life. Half-life, that's a measurement of what? Is that speed, time, energy, mass, weight? Half-life is a measurement of time. Time. It's a measurement of time. It's the amount of time it's going to take for half of my sample to decay. All right? It's the amount of time it's going to take for half of my sample to decay. Okay? So that is half-life. So on the next slide, if you guys are following along with me on these couple slides, hopefully you guys are. If we look at this picture, this is hopefully what you are going to see today when we go back and look at our M&M lab. Okay? Do you see at first I start with 100% of the unstable parent? So I start up at the top with 100%. At time 0, has any decayed? No. But after one half-life, how much has decayed?
50%.
50%, right? 50%. So in this picture, it does grams or atoms. So you're right, 10 half decayed. After 2 half-lives, I now don't have 50%, I have 25%. So if I have 25% that are now unstable, what percent is now stable? Nice and loud. 75%, right? Because that's to always add back up. Conservation of mass, conservation of matter. I can't destroy anything, right? So as it's going through those decay processes, it's decaying into a more stable element or a more stable isotope, okay? So as we're going through this, we're going to keep decaying until I almost have how many radioactive atoms left? What number am I going to get really close to but not touch? 0, right? So ultimately, I'm not going to have very many radioactive atoms at the end. So with that, so on Friday, we did this. We're going to be graphing that today, see if ours mimics this radioactive decay. I had mentioned, though, on Friday that we can use this understanding that atoms decay in a set process so that we can date things that are really old, okay? We weren't here with the dinosaurs. So we don't know how old the dinosaurs are. If I just see bones and be like, it's kind of old, right? It's not how it works. If I look instead at the percent remaining of the radioactive substances, I can kind of work backwards and figure out how old it is. So in order to figure out how old something is, if I look at this first one, it says carbon-14 has an approximate half-life of 6,000 years. How much of a 30-gram sample would remain after 18,000 years? Well, how much am I going to start with? How many grams? 30 grams. Anybody know? So if I'm starting with 30 grams, how long does it take for me to go from 30 to 15? Yeah, it takes 6,000 years. Because it says the half-life is 6,000 years. So then, have I reached my total time of 18,000 yet? No. So each arrow represents a half-life. It represents the time that it takes for half of my sample to decay. Okay? After another 6,000 years, how much would I have? 7.5. Yeah, I'd have 7.5. Have I hit 18,000 yet? No. So as I'm going through, I'm going to put my amount of time above the arrow, okay? So that I can go through and be like, oh, that's 12,000 years. I'm not quite done yet. I need one more half-life, 6,000 years, and I get how much? 3.75. Good. So after one more half-life, 3.75. So now the question is, if I only have 3.75 grams left of the parent isotope, which is our unstable one, where did the rest of the 26.25 grams go? It got converted into what? Not the unstable, but now the stable. Not the parent isotope, but the daughter isotope. So remember, the total mass always has to be the same. So the parent is going to decay till it gets really, really close to 0. And then the daughter is going to increase in amount. It's going to keep increasing, because as time goes on, more and more is going to become stable. All right, so check out this one. This one says if only 12.5% remain after 150 years. Well, I'm ending with 12.5%, right? That's the percent of the unstable nuclei. What percent would I have started with? What percent would I have started with? At time 0, would anything have decayed? No. So what percent is that? 100%. See, you guys are so smart. So I start at 100%. Then what's half of that? What's half of that? What's half of that? 12.5. So when I take those halves and I go from the 100 to the 50 to the 25 to the 12.5, that whole process took a total of how many years? Where'd you get that number?
What? Never mind.
No, that's okay. I was just curious. How did you get the number?
No, never mind. I tried. I tried to divide 150 by 4.
I like your thought process, but you don't divide it by 4.
Yeah.
How many half-lives have there been? There's only 3. 1, 2, 3. So that's totally okay. That is our most common mistake during this. Is a lot of times people will count 1, 2, 3, 4 half-lives, when really you got to count the arrows. So the arrow represents when it goes down by a half, right? This is the starting amount. So when I take a half, that's been 1 half-life. Half, 2. Half, 3. So on that one, you're right. I would take 150, and then I would divide it by the 3 total half-lives. So 1 half-life will be how long then? What's 150 divided by 3? 50. Yeah, so the answer to that one is 50 years. You got it.
50 years to do that.
Yeah, 50 years. All right, this one says, well, what frictional amount would remain after 6 half-lives? So since it tells me 6 half-lives, that means how many arrows do I need? 6. Okay, so if I'm doing fractions, if I was doing percent, I would start at 100. If I'm doing fractions, what would I start at? 1. What's half of 1? What's half of that? What's half of that? What's half of that? What's half of that? Whoa, slow down. How many half-lives has it been? 6. So I start out with 1, and then I got to do a half of 1 is 1 half. Half of that is a 4th. Half of that is an 8th. Half of that, 1/16, 1/32, and then 1/64. All right, so let me see if I can ask you this harder question. So that means after 6 half-lives, I have 1/64 of my original sample remaining. How many 64ths would it be of the unstable, of the stable? I have 1/64 remaining of the unstable. How many 64ths would be of the stable? 63 64ths, right? Because it has to add up to 1, right? It has to add back up to 1. So does everybody see that? That if I have 1/64, then that means 63 64ths is of the stable daughter nuclei. All right, good. All right, so that's kind of just the introduction to half-life. We had started to hint at this from Friday, the idea that we can use the understanding that atoms go through a decay process. It takes so long. And with that, we could backtrack and say, okay, well, how old is that actual substance? Because unfortunately, our life is limited with how many years we actually live. We can't kind of work backwards, go backwards in time, except if we were using the radioactive isotopes. Okay? All right, so will you grab your M&M lab? So go ahead and grab your M&M lab. We are going to finish it, and we're going to take a look at one of the parts together as a team. So with our M&M lab, you guys were looking, we did 2 trials, and we shook the actual cup, and we said, okay, M side represented the unstable nuclei, which was the parent. The blank side represented the daughter nuclei. So as we got our data, you guys finished filling in the chart, right? Yeah. Yes. All right, so mine, I'm going to show you mine. This is the if you were absent version that I'm showing you. This is my data. Obviously, your data is a little different than mine. Let me see if I can just download it. All right, so looking at that data, the first thing you guys are going to do is go ahead and start building your graph. So on the x-axis, it says half-life. So I'm going to write half-life on my x-axis right here. So it's going to say half-life. My suggestion to you is every other line is 1 half-life. So I'd have 0 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know if any of you guys went more than 10. If you went more than 10 half-lives, then that's fine. If not, then you can put fewer. On the y-axis, you are going to have percent of candies remaining. And on that one, I suggest every line go up by 5. So 5, 10, 15, 20, 25, 30, all the way to 100. So I'm going to give you guys a second to go ahead and do that. By the time you're done, yours should look like this. It should be set up just like this. Set up just like this. What's that? Y-axis, go up by 5. It's your percent of candy remaining.
My notability deleted, so I had to reinstall it, and now I lost everything.
No. Do you have it backed up to the cloud?
No, but I know.
Wait, they go up by 5, you said?
Yeah, go up on the y-axis by 5. X-axis, I did every other line up by 1. The reason I did that, that's just going to stretch my graph out a little bit. That's fine how you did that. This is what mine's going to look like. So y-axis up by 5. X-axis, every other line up by 1.
Every other one?
Does it go up by 5 like that?
Yep, up to 100, good, and then, yep, that's fine.
What do we label it?
X-axis is half-life. Y-axis is percent of candies remaining. All right, so on your data table, half-life right here, everybody take a look up here. Half-life right here, this is my X value, okay? So if you're looking at your chart, you have half-life is X. The average percent over here is going to be your Y value. Everybody has the same first point. Everybody starts at 0, 100. So go over 0, go up 100, put a point.
Wait, we have to, this is on the Y, so we have to go all the way up to 100?
Yeah, but you went up by 5s, right?
Yeah, but
That's okay. All right, and then based upon my data, I would go over 1 half-life, and I would go up by 55. So this is my X, Y coordinate. So I'm going to go over 1, up 55, put a dot. And then I would go over 2, up 24, because that's my data. You guys are using your own data. You're going to use your own data.
Wait, the graph, you said the y-axis each point.
Yeah, step by 5. All right, so go ahead, start plotting your points for your half-life and your average. And then once you get those points, you can connect the dots. Everybody's final point is going to be a Y value of 0. And hopefully your graph looks a little bit better than mine. But do you see mine is going to be a curve? This is exponential decay.
yeah, mine's.
Yep, looks like it's set up right. Now go ahead and start plotting your points. And then connect those dots. Connect those dots.
Wait, I'm still up.
Oh,
So I have
Yep.
6.
okay, so this is your X.
Okay.
There's your Y. So over 0, up 100. Over 1, up 48. Over 2, up
Oh,
28.
it's just the number of half.
Yep. So it's your X. So you go over 0, up 100, put a dot.
Alright, I finished.
Yep. Over 1, up 48. Okay. All right, so your graph, like I said, should look something like this, exponential decay. You should have a nice curve, That's okay. So this is going to be, this is your x, this is going to be your y. So we're going to go over 0, up to 100, put a dot. So on here, you want to each line is 5, 10, 15. Okay, so you want to add that because this side has to go up to 100. Okay, so go ahead, fix that one, and then I'll make graphing a little bit easier. So once you have that nice graph, you're going to have a nice little curve. So that's your x, there's your y. So over 1 now, up 55.
Can I see what
Over
your graph
1,
looks like?
up to 55, put it
Can I
down.
see what your graph looks like?
Over 2, up 18. Yep, you got it? And then connect those dots. So like I said, you should have a nice exponential decay where it's going down.
Like this?
Yep, oh, look at that. That looks so nice.
So I connect it?
Uh-huh. This is your x, there's your y. So over 0, up 100, put it up. Over 1, up 48, put it up. Because this is your x value. So that's x and y, just like if it was a normal point that you're plotting on a graph. Okay. No, you do not have to do an arrow. You can just connect your data. All right, so you see how yours is really, really crunched there? That's why if you went every other, it would spread it out just a little bit more for you.
27%.
All right, so once you have that graph, if you are looking at some of the questions afterwards, the first question asks about, okay, well, we stopped at 0. Is that accurate when we're actually looking about half-lives? Is that true? No, right? It's not true because it's not possible. It's not possible for us to reach 0. So since it's not possible for us to actually reach 0, did our data do a pretty good job at representing half-life, having a nice curve, decreasing by a value of a half? Yeah. But we did reach 0. We did reach 0. We did not take any of our actual M&Ms and cut them in half and keep cutting them in half and cutting them in half and cutting them in half.
When do we get to an atom if you keep doing that?
So once you get to an atom, so remember, in terms of half-life, it's a percent or it's a mass, not individual atoms. So at that point, there's so little remaining that it wouldn't be even detectable for us. It would be too hard for us to do that. Okay? All right, look at question 2, though. Question 2 says, well, if 50%, if you are still trying to graph, I will come around and help you guys here in a second. But let's try these last couple questions. So number 2 says if 50% remains after 4,000 years, well, what is its half-life? Well, how much remains? 50%. So is that its half-life? Yeah, so its half-life is? No, 4,000 years. Remember, half-life is a value of time.
So it's half time. Wait, what?
So the answer to number 2 is 4,000.
What's the point of half-life?
It helps us be able to identify age of substances.
Can we just guess?
No, we can't just guess. Oh my gosh, this is science. We like to be precise and accurate.
That's the oldest person in the world right now. Go ask her, were there dinosaurs when you were growing up?
Okay, but that makes it a very limited to like our human existence, right? It limits us.
You weren't born then. You never know.
All right, guys, help me out. Come on, remember, I'm trying to tape this for next period, so they have it. So help me out. Number 3, half-life of a certain radioactive element's 1,250 years. So that means every 1,250 years, the value or percent of radioactive material goes down by a factor of 1/2. So since number 3 is asking about a percent, what percent would I start out with?
Well, can we see what you're writing?
100%, right?
We can't see what's writing.
I know, I have to record it, dude. I'm writing it on the board for you guys. All right, so 100% is where I'm going to start. After 1,250 years, what percent is left? 50. Have I hit my total time yet of 7,500 years? No. All right, after another 1,250 years, I now have what percent? 25. After another 1,250 years, what percent do I have? 12.5. Oh my gosh, after another 1,250 years, I have 6.25.
Then after I got 3.
Do you see I have 5,000 years right here?
Yeah.
Have I hit 7,500 yet?
No, you need 2 more.
I need 2 more, so that's going to give me what?
12.5.
3.125? And what's my last one? You guys going to have to help me out.
That's too long.
1.5625, I think. Okay, close to that. All right, so each time that you're taking a half, okay, each arrow represents 1,250 years. So each time it's going to go down by a value of 1/2. So on this one, I had to go through a total of 246 half-lives in order to reach my total time of 7,500 years. Okay. So my final amount on this one, 1.5625, is my answer. Okay. All right, 4 I think is a little bit easier for you guys. So if I look at 4, 4 says the half-life of a certain substance is 800 years. How old is it if only 12.5 remains? Well, 12.5, look. Shoop. Look at that.
3,200.
All right, so 1 second, hold on. I start with 100 because it's asking for percent, right? So anytime I have percent, I need to start at 100. I keep taking a half till I reach the end point, which was 12.5. Each arrow represents how many years? 800, good. So what's my total time then? 2,400 years. All right, so to help you out, is it possible for me to live 2,400 years old? No. So that's why I can't just guesstimate and be like, it's like old, it's like skeleton, it's dead, you know, it's been a while, I don't know, right? I can't guess it. I want to get an actual amount. Okay? So if you have your graph done and you now have the post-lab questions because we did them together, okay, you can submit it to your M&M lab. Okay, so once you have that done, if you have to fix your graph or get help on your graph with me, that is fine. Okay? For today then, so you guys have been having questions with these half-lives. Let's actually try it. Let's try some practice. Let's see how you're doing. Okay? So I have for you a small practice on Canvas. It is only 10 problems. Okay? I don't often say, hey, I want you to finish this for homework. Okay? I do want you guys to do this. You might be able to bust it out here in 17 minutes, but I want you to try this. Now that we just talked back over the M&M lab, we introduced it again with our bell ringer. Can you do it? Okay, this is going to help you figure out, hey, I got it. It makes sense. I'm taking a half. I'm taking a half. I'm taking a half. If you do that and you're like, hey, I feel like I'm pro level status, try the concept check. Okay? Try the concept check. All right, so today, have to try the half-life practice. If you're working with a friend, that is fine, but you are doing your own paper. You're doing your own work, so you both are practicing it, okay? All right, questions? All right, go.